Okay, this is Dr. Holt. I want to work 3 two-dimensional collision problems. The first one, we have a pool game. The cue ball, which has an initial speed of 8 meters a second, makes an elastic collision with an 8 ball, which is initially at rest. After the collision, the 8 ball moves at an angle of 30 degrees to the original direction of the cue ball. We want to find the direction, motion of the cue ball after the collision and find the speed of each ball. Assume that all balls have the equal mass. Alright, key words here, we have elastic collision. So when we have elastic collision, there's a few things we do know. We know that momentum, the vector quantity, is going to be conserved. And we know that kinetic energy, which is a scalar quantity, is going to be conserved. So we do know that. So what I like to do is set these problems up as, and draw a picture, and this is going to be my initial condition, and this will be my final condition. Now, one thing you're given, this angle here is 30 degrees. Now, if this angle is 30 degrees, and this only if the masses are the same, then the angle between the angle between this velocity and this velocity will be 90 degrees. Now, I solved that in a mathematical proof on an earlier video that I posted on YouTube, and that would be useful for you to watch if you're confused at all about where that's coming from. But again, that's only if the masses are going to be the same. Alright, so what we can do here is establish what our initial momentum is going to be. Our initial momentum, again, that's a vector quantity, and the x will equal to the mass times the velocity, and that gives me 8m. Now we know immediately that Pf and the x will also have to equal to am. That has to be conserved. We know the momentum initial in the y here is equal to 0, so we know that the final momentum in the y must also equal to 0. And again, we know that kinetic energy is going to be conserved in all situations. So we could say right now that the kinetic energy initial is going to be 1/2 times m times h squared. And again, that's scalar quantity. The directions is not important. H squared is 64. That gives me 32m. I'm not sure we're going to need that, but we'll find out on this problem. Alright, so we know this, and we know this, this, and this. Okay. So let's go ahead and start out with momentum. Again, we'll do the momentum in the x direction first. I'll make it p in the x. We know that that has to equal 8m. So we go back to this, and can we not say that this mass, which is just going to be m, times the velocity times the cosine of 30 degrees plus this mass, and I'll make this a velocity of 8 too. The velocity of the cue times the cosine of 60 again is equal to 8m. Now our masses are going to cancel out. Excuse me. Alright, now we'll go back and do the momentum in the y direction. Again, we know that's equal to 0, so we have to this momentum in the y has to be equal to 0 also. So we'll get mass of the 8 times the velocity of the 8 times the sine of 30. And again, that's momentum is a vector quantity, so be careful with your direction. I'm going to make that go negative because it's going, it has negative the momentum is going in the negative direction. Excuse me, the velocity is going in the negative direction, so the momentum will be negative. So we got minus m times velocity of the cue times the sine of 60 degrees. Okay, again, I can divide by masses because if I divide this side by m, I also get 0. So masses are gone. Alright. So let's just scroll down. Let's go ahead and rewrite our equations. And we're going to have 8 is equal to V8, and I'll have the cosine of 30 here, plus velocity of the cube, cosine 60 degrees, with that equation, and then the other equation we'll have is 0 is equal to V8 times the sine of 30 minus velocity q times the sine of 60. Okay, so those are two equations right here. Now you ask yourself, how many unknowns do we have? We have two unknowns. We don't know V8 and we don't know VC, but I have two equations, two unknowns. Again, there's several ways to solve this. Solve with the matrices, substitution, elimination. There's many ways you can do this problem. I'll just do it with substitution here. I'm going to take this equation. We'll just solve for V8. V8 times the sine of 30. Move this to the other side is going to equal to V cubed times the sine of 60. Correct that. So V8 is going to equal to the velocity of cube times the sine of 60 divided by the sine of 30. All we have to do now is take that value right there, put it back in to the first equation right here. Alright, and now we'll rewrite that and we should have the problem nailed. 8 is equal to VC. We got the sine of 60, so I'll write it all out. Now you can convert that to the cotan if you wanted to. Sine of 60, cosine 30 over to the sine of 30 plus VC cosine of 60. Alright, so we'll run these numbers real quick. Alright, here we go. So I'm going to take the sine of 60 times the cosine of 30. Do it real quick. Cosine of 30 divided by the sine of 30. So right here, this will give me 1.5 VC plus cosine 60, which will be 0.5. VC is equal to 8. So that gives me basically 2 VC is equal to 8. So now the velocity of the cube is going to equal to 4. And again, what were our units? I believe they're meters per second, were they not? Yeah, meters per second. So that's going to give me MC. Sorry, meters per second. So now we know the velocity of the cube. We put it right back into here. Take that value of 4. We'll multiply it times the sine of 60 divided by the sine of 30. And that gives me the velocity. I'll do it in black. That is equal to 6.93 meters per second. Okay, that's how we get our two velocities. Now let's go back to our problem, see what else we need to do. So now we know the direction. Again, that was the first part there. It was 60 and 30, and we find the speed of the ball. Assume that the balls have equal mass. Alright, so again, not too bad. The most important thing to note is this information right here. This is what's going to help you solve these problems. This part right here, and also noting that the angle here, again, that's only if the masses are the same, will be 90 degrees after the collision. Alright, let's look at another problem. This problem here, I have a puck, a mass 0.6 kilogram, approaches a second identical puck that is stationary on frictionless ice. Initial speed moving is 4 meters a second. After collision, one puck leaves with a speed at 30 degrees original. The second puck leaves with a speed v2 at 60. And again, that's because the masses are the same. We want to calculate V1, V2. Alright, so let's work this problem here. What we're going to do with this one, again, come back to momentum in the x must equal to momentum final in the x. We have that, and we know that momentum initial in the y must equal to momentum final in the y. Alright, so we know the initial speed of the moving puck is 4. So can we not say that P initial in the x must be equal to mass times velocity, which will give me 4m. So I know, and I know immediately that the final momentum in the x must also be equal to 4m. Here again, there's nothing moving in the y, so momentum in the y must equal to 0. So final momentum in the y must also equal to 0. We work the problem. We should be pretty easy. We got 4m. We'll do the x part first. I got 4m here is equal to mass here times the cosine of 30. And again, this problem is almost identical to the one we just did. Yeah, I've left out my velocity though. Let me do that real quick. That'd be velocity 1 plus mass times velocity 2 cosine 60. That's the first equation there. Second equation, 0 is equal to mass times V1 sine 30 plus mass V2 sine 60. Okay, and all we have to do is solve for our velocities. Alright, what I'm going to do with this one, I'm going to do a little different. I'm going to do this one with a matrices just to give you a little variety. I'll set this up as V1, this will be V2, and this will be my values over here. Alright, so we take this one here, my leading coefficient, and now you notice too, let's just do this, the masses are all going to cancel out every one of these problems. Alright, so my leading coefficient with V1 here is going to be the cosine of 30, V2 cosine 60, this one will be 4, this will be 0, this will be sine 30, and oops, make one mistake. I caught a mistake right there. Sorry about that. That'll be negative. And that'll give me this one negative sine of 60. Alright. So we'll set that up in the matrices. Again, it's a 2 by 3. I got 2 rows, 3 columns. So I'll go to my calculator. Let's do this real quickly. I got a 2 enter, 3 enter, I got 2 by 3, and I just put in the values. Cosine 30, cosine 60. I got a 4. I got sine 30 minus sine 60. I got 0. Second matrices. Just about got this done. Okay, and what that gives me when I do that in the matrices, and again, you don't have to do it this way. You could do it by substitution. That gives me V1 as 3.464 meters per second, and V2 as 2 meters per second. Alright, now, I didn't cover those up. Actually, there's the answer right there. You can just prove. I made the proof. Second question, is the collision going to be elastic? Alright, what we want to do then, remember kinetic energy is a scalar quantity, not a vector quantity. So we'll find out how much kinetic energy I had initial. Alright, and again, the puck had a mass of 0.6. I could have put that back in this equation too, but the masses were the same. So I left that out. Okay. Go back to our original. We had a velocity of 4. Okay, I'm going to leave the masses out because again they're going to cancel out. You can put them in if you want. It makes no difference. I'm just going to put it as m. My velocity was 4. That gives me 8m. That's my initial kinetic energy. Now we'll do our final kinetic energy. Okay, so our kinetic energy final, we'll just go back to 1/2 times the mass. We take this 3.464, we square that, plus 1/2 the mass times 2 squared. Solve that, and that's, run that number and you'll get 8m. So the mass is, the kinetic energy is conserved. If the kinetic energy is conserved, we have an elastic collision. And since I have the answers right here, was it? Yes. Alright, do one more problem. This one here, I also have the answers, and I'll prove to you how to solve this one here. Alright. The figure says the figure below shows a collision between two objects of equal mass. Now this one is showing you what happened before and what happened afterwards. Alright, so you're going to work this basically the same way. You say, what is the momentum in the x direction initial? And in this, the only thing I'm going to have is m times 3 VO. I have no other. This one's not moving, so that tells me immediately that px final momentum must also equal to 3 mVO. Now ask yourself, what is momentum in the y direction initial? It's 0. Nothing's moving in the y direction. So that tells you immediately that the final momentum in the y must equal to 0. Alright, so we'll work the problem here. We'll do the x first. That gives me 3 mVO, which is I have initially. We got to break this into components. Now this one, they tell you the angle is the tangent of 10. So let's just draw a quick little, just do a little sketch over here. You don't, I mean, this will make, I think, perfect sense to you, but if you don't want to convert this back to the angle, you can just do it with ratios, right? If this is 2 and this is 1, then using Pythagorean theorem, 2 squared plus 1 squared, take the square root, that would give me the square root of 5. So the cosine would be 1 over the square root of 5, and the tangent, or excuse me, the sine would be 2 over the square root of 5. So I come back down to here, I take this mass, I multiply it times this velocity, which is square root of 5 times VO. Now we do the x component, so we do the sine times 1 over the square root of 5. The square root of 5's cancel out here and here, so we just add m times VO. Now we come to here. This has a value of 2m. It has a velocity of v2. Okay, now instead of using the cosine, I'm just going to say v2. I'm going to make this into the v2 into the x direction. And at the end, we'll go ahead and figure out what the angle is going to be. Okay, now we'll go back to the y. We know that it has to equal to 0. So I'll do the m. Again, I'm going to go ahead and put in the velocity, the square root of 5 times VO. Now we use the sine. The sine is going to be 2 over the square root of 5. Square root of 5's cancel out. Now this one has going down, so we'll make it minus 2m And now I'm going to just make it v2 into the y. That's this y component of this velocity. Again, this is the x component of this velocity. You notice here I can cancel out a lot of stuff. Cancel out masses, here, and here, here, here. Because I can cancel out this because, again, divided by m, 0 divided by m is still 0. So rewrite the equation, and we should have this problem done. 3VO is equal to VO plus 2 V2 in the x. So first equation, here we'll get 0 is equal to 2 VO, because I got 2 there, minus 2 V2 in the y. Alright, so there's our two equations. Alright, we'll take the first one, we'll solve for V2x. So we got 3VO minus VO. And then all we have to do is divide it by 2 is going to equal to V2 in the x component. 3VO minus that's 2 divided by that gives me VO. So we know V2 is equal to V2x in the x direction is equal to VO. We do the same thing down here. Move this to the other side, multiply by negative. Doesn't that tell me that 2VO is equal to 2V2 in the y? So doesn't that tell us that V2y is also equal to VO? Alright, so what we have is it has two components, one going this way, one going this way, and it's going down this way. Alright, boy, I'm having trouble drawing straight lines. Alright, so both of those are equal to VO. VO. So now if we want to find the magnitude, obviously the magnitude would be this way here. Now, since these are the same, this angle here has got to be 45 degrees, right? Because the tangent, if the components are basically a 1-to-1 ratio, then tangent of 1 gives you 45 degrees. We know that. And let's see what else we're looking for. We're looking for the magnitude. Well, isn't this velocity here just going to equal to the square root of this one squared, VO squared plus VO squared, which gives me the square root of 2 VO squared, which gives me the final velocity is equal to square root of 2 times VO. Okay, so there's your final velocity, and there's your angle. And that's how we get this one and this one. Alright. So there are 3 two-dimensional collision problems I solved. Again, I hope you find these pretty straightforward. The most important thing on all of these is use the conservation of momentum. You can use that whether it's an elastic or inelastic collision. You can use the conservation of, or that you can state the kinetic energy will be conserved only in an elastic collision. Excuse me, only in an elastic collision. In an inelastic collision, you cannot state the kinetic energy will be conserved. Alright, best of luck with these problems.